Hello and welcome. My name is Ian, and in this video, I'm going to be continuing the discussion about the foundations of probability and statistics for analyzing data. And in this video, I wanted to talk about how we characterize, and represent, and describe data in different ways. And I'm going to start with this idea of binning. Now, if we take a look at this example that I showed in the last video, where we have a random variable that's corresponding to the result of multiple coin flips, where each result, heads or tails, represented with a simple number 0 or 1. And what we can do is divide up this data in different ways. And one of the most logical ways might be to count the number of ones that we got in these 9 coin flips and count the number of zeros that we get. And this is called binning. So we basically have 2 bins or buckets, one for the ones, one for the zeros. And we've counted up all the ones. We see that there are 5 in this particular experiment and 4 zeros in this experiment as well. And this is one way that we can use to simplify or describe this data a little bit. We can also do this with the multiple die rolls example. So we performed an experiment, we got different results, a 1, a 5, a 6, and so on. And we can also bin these results. So we have a data set here, and one way we could bin it is, for example, divide it in 2 like we did with the coin flips. And the way we could do this with the die is assign 1 bin to all the even results and assign another bin to all the odd results. And if we count them up here, we see that there are 7 evens and 5 odds. But there are different ways you could bin. So we could also, again, divide into 2 bins, but instead of doing evens and odds, we can do the results 1 through 3 get assigned to the first bin, and the results 4 through 6 get assigned to the second bin. Or we could do 3 bins. So we could do 1 through 2, 3 through 4, and 5 through 6, respectively, into these 3 different bins. And what we'll see is that the ways that you divide up your data make a big difference in your understanding of it. So let's say we were trying to figure out, for example, if this is a biased die by conducting some experiments, getting some data. And we could imagine a situation perhaps where the die is heavily biased to roll either a 5 or a 6 with equal probability. So maybe we have, double the chance of rolling a 5 or a 6 compared to a 1, 2, 3, or a 4. Now, since 5 is odd and 6 is even, if we had binned the data by evens and odds, then we would not really notice anything suspicious occurring. So we would see relatively even proportions of 5 of evens and odds, regardless of the fact that 5 and 6 are both more likely. If we had instead, though, used this third binning strategy down here, where we have the 3 buckets and the last one corresponds to 5 and 6, then maybe we would see that that there's a disproportionately high number that we're getting for this last bin. So that's discrete data, and let's talk now about continuous data. And what we'll see is that binning is not just useful in general, but it's essential if we want to, for example, visualize continuous data. And so here's an example of a data set for a continuous random variable. And we can see that we have different values here, so 3.68, 10.95. And what we can do to better understand this data is we can break it up into bins. So here we create 3 bins. bin 1, bin 2, bin 3, and bin 1 corresponds to any data falling within the range 0 to 10, bin 2 from 10 to 20, and then bin 3 from 20 to 30. And so if we go through each of these data points, so the first one, 3.68, well, since this is between 0 and 10, we assign it to bin 1 here. And we can do this for all the other bins that we have in all the other data points that we have in our data set. And what this then allows you to do is visualize the data using a histogram. So since we binned it, we can have an x-axis here, a horizontal axis that is corresponding to our bins. So we have the range on the bin markers here. So 0 to 10, 10 to 20, and 20 to 30. And what we can do is assign a count or frequency to each of these bins. So we've counted, if we count them. So for example, we have 2 instances where we had a 1, bin 1. We had 4 instances of data points falling into bin 2 and 1 instance where the data point fell into bin 3. And so those then become the heights of our histogram here. And so this gives you a very quick way to visualize how this data was distributed throughout the range of possibilities. So how are histograms or frequency distributions or frequency distribution visualizations, they could be called, how are histograms different from bar charts? So they look very similar. In a bar chart, though, you only have height. So if we look at this example for the number of coin flip results on the horizontal axis here, we do not have any numerical values. We have a category, heads and tails, and we see that the height here is the only piece of information other than the category here. But if for example, we made the bar larger or fatter, or if we swapped the order, for example, this would not really matter. And a histogram is distinct from a bar chart, therefore, in that this x-axis actually means something. So we have, for example, a time here. So we have a variable, and that's going to be spanning this range here. And the other consequence is that the area of some of these bars actually means something as well. So since we have both a width and a height, the area has an actual quantity. So it's not just the height as you have in the case of the bar chart. So what histograms allow you to do then is to communicate information about frequency distributions. And one thing that is very common is needing to compare data sets. So here we have an example where we have 2 proteins, protein A and protein B, and we're interested in the distribution of protein A when it's complexed with protein B, so stuck together like this. And we have a setup here where we're looking at the particle size distribution. So maybe we have a light scattering instrument or something that allows us to get an idea of the size of stuff in our sample. And we have a sample of just protein A here, and we see that we have a count here, a frequency of how much of a particular size particle we have in this sample. And so we can see that around 50 nanometers diameter here, we have maybe the peak of our protein A. And then we have the same for protein B here. And visualizing it, we see that the peak here is maybe closer, maybe a bit smaller than protein A. And what we're interested in is, what does it look like when we mix these 2 samples together? And so we have a third histogram here where we're looking at the complex, and then we see 2 populations and one peak that is larger and cannot be explained by just one of these constituent samples here. So this is maybe indicating that some of these proteins are sticking together. So we have a lot of information that's conveyed here with these histograms, and that's the power of being able to bin and kind of break up our data. We also have a number of other ways to visualize data. So one of these is smoothing. So if we take data sometimes to kind of simplify or reduce this information, what we can use is smoothing techniques. So one example is kernel density estimation. And this can be a way to take frequency data, binned data, but then kind of remove some of that noise or that blocky effect that we may have with the original binning. And sometimes interesting patterns come out, or maybe you see something useful. We also have the box plot. So instead of having 3 charts like we had in the case of the histogram, box plot is convenient in that it allows you to compare distributions side by side. So here we have 3 frequency distributions displayed on one chart. So here we have protein A, protein B, and the complex. And the box plot is really trying to simplify information. So instead of showing every bin, every little partition that we created from the data, we've broken it down to some characteristic statistics. So we're representing the middle of each of these distributions with the median, or the point corresponding to the 50th percentile, and the bottom and top of these boxes corresponding to the 25th and 75th percentile. So 25% of the data is either below or above these points. And we can use these interquartile ranges here to define outliers, points that are lying mostly outside the distribution. So for example, these are often defined in terms of fractions of this interquartile range. So for example, the Q1 here minus 1.5 times the interquartile range could be one definition of what constitutes an outlier. We can also use violin plots. So this is something kind of in between the smooth histogram and the very simplified box plot. And what it allows you to do is, again, like the box plot, we can compare distributions side by side. So that's nice because, in the case of the histogram, we had to make 3 plots. And in this case, we have a more easily comparable. So we can see, the middle of this peak is occurring above the middle of this peak. It's much easier to see that. And also, unlike the box plot, we have information about the shape of the distribution. So for example, this third category here in the box plot, we would not have been able to see that there are actually 3 peaks here. And this might be important information for our understanding our sample. So depending on your situation and what you're trying to convey or trying to understand or communicate, different visualization techniques may work better than others. So that's visualizing data, and often we want to describe it as well. And one of the basic ways we can do that is with the arithmetic mean. So now, instead of reducing our data to a set of bins, we're reducing it even more to just a simple number. And if we have, say, a data set here, so we have n points in our data set, and these are different data points, so x1, x2, x3. And we can, of course, compute the arithmetic mean. And everyone knows this, I'm sure, but we're just going to take the sum of these points and divide by the total number of points here. So here we have x sub I here representing 1 point in this data set, and then this summation indicating that we're going to sum over all of these points. And then n here, the number of points, so we're dividing by this. And then we'll use this notation, x bar here, usually to represent this arithmetic mean. What you might be less familiar with is the weighted mean, or the idea of getting a mean from binned data. And how this looks is we'll have another summation here, so it starts out very similar to the arithmetic mean that we have in this example, but now we're dealing with binned data. And so we have, instead of individual data points, we have x corresponding to the label on a bin, and n corresponding to the height of that bin. So we're multiplying, we're taking the product of each of these bins times their height and summing these up, and then again dividing by the number here. And to visualize this, you can imagine, say we're, we have, say, a bin label here. So this could be, for example, the average maybe of the 2 points spanning the range of this bin. And we have the height, or the count or frequency corresponding to that bin. And if we sum up all of these products, then that will also give us the arithmetic mean. So here's an example where we do this. So we have a single molecule microscopy experiment, binding experiment, and we're trying to check how many times a ligand binds to 100 enzymes that are on the surface. And here we can set up our binding events and our counts here. So we have 70 cases here where 1 binding event occurs, 20 cases here where 2 binding events occur, and 10 cases where 3 binding events occur. And we want to know what is the mean number of binding events per enzyme. So here we have x, this is our random variable, number of binding events. And here we have n, which is our frequency, or our count. And here's our formula for the weighted mean. So we can go through and just compute all of these. So, right, we want this quantity for each one of these bins. So it's 1 times 70 for the first bin, 20 times 2 for the second bin, and 10 times 3 for the last bin here. And then again, we're dividing by the n number of points that we had. And if we do this, then we get the arithmetic mean, 1.4 binding events per enzyme. So we have, in addition to the arithmetic mean, we have other ways to describe data using a single number. And these are often known as measures of central tendency. And the reason we have these in many cases is because the mean is not a perfect descriptor, and there are a lot of situations where the mean might be misleading. So for example, we have this data set here, and if we were to take the mean of this data set, we would get this large number here. And depending on what you're trying to say or represent with this descriptor, this may be misleading, right? So if I wanted to know, for example, if I'm going to reach into a hat and pull out one of these numbers, maybe what I want to know is what am I most likely to see when I pull that number out. And if we just go by the mean, then this would not really be necessarily a good representative indicator of what I'm likely to pull out. So in some cases, we might be better off using the mode. So the mode is the most popular value. For example, we roll a fair die multiple times, and we rolled a 5. We got a 5 16 times in our data set. And since this was the most frequently occurring result, we would call this the mode in that case. You also have, for example, the root mean square. So this is used for situations where some of your data is positive and some of your data is negative. So for example, we could consider an alternating current, and we want to know the average amplitude, for example, of this alternating current. And so alternating current can be positive or negative, and it's oscillating between a positive value and a negative value. And so if we took the mean, if we took several measurements, for example, of the current, we might see that sometimes it's negative, sometimes positive, and the mean might turn out to be close to 0. So the mean is not really appropriate for this situation. But what we can do is square each of the quantities. So the negative numbers become positive, the positive numbers stay positive, and then take the square root. This should be like this, actually. We can take the square root of this in order to get back to the original units. And that way we have an idea of the average amplitude of this current. And if it's a large amplitude, we're not going to just have these positive and negative values canceling each other out. Another measure of central tendency to consider is the median. So we mentioned this earlier with the box plots, is like the halfway point in ranked data. Or another way to think about it is half of the data falls below and half of it above. So if we did this with binned data, for example, we would be able to count that half of the data is occurring above and below the bin that we choose here. If we take this first example here, so we just rank the data, and we see that half of the data is up here and then the other half is below. So the median would be then like the average of these 2 points, 1.4 and 1.5. So that's measures of central tendency, but we have some limitations there as well. So another limitation of the mean, for example, happens in bimodal distributions. So let's say we have two data sets here, one that's got these two peaks here and one that's got only a single peak. And it might be, in this case, that the mean is actually the same for both of them. So like around 60. And if this is the only number that we're presenting, then this could be losing a lot of information that might be important for understanding this system. And so we kind of want another descriptive statistic that we can use to represent how much the data is clustered around the mean, or in other words, the spread. And so you probably know where we're going with this. So we, of course, have variance and standard deviation that we use to describe spread. But what I want to do here is kind of talk about the origins of these measures and the intuition behind them. So what is the variance? What is the standard deviation? And I think one of the best ways to understand it is, let's try to imagine what would be a good measure of spread. If we were to be inventing statistics from scratch ourselves, how would we go about it? And one thing that would maybe make sense is maybe we want a value that's like the average distance that a point is from the mean. If we were to grab any random point in our data set and ask, on average, how far is it from the mean of this data set, that would give you a good idea of the spread of the data, how much it's spread out. So we could attempt to try to do something like this with, we go through each data point, x sub I here, and subtract the mean. And then we sum these up. So we're going to take the arithmetic mean of this and divide by n. And what we'll see is that this is sort of problematic because if we take the difference between every data point with the mean, then those that fall below the mean are going to be negative, and those that fall above the mean are going to be positive. So it's kind of similar to this alternating current example where we have negative values and positive values canceling each other out. So this doesn't really give us a good idea of the distance, the average distance a point can be from the mean. It's not helpful. But this is exactly where the idea of the variance comes in. So in order to deal with this problem of negative and positive canceling each other out, what variance does is you square this quantity. So we take the difference of each point from the mean, and then we square it. So the negative differences become positive, the positive differences stay positive, and this way we get an actual idea of how far stuff is from the mean. So this, I think, is the easiest definition to remember. But you also have these other definitions. So just kind of algebraically rearranging this equation here. So you can get, for example, the average of the squares minus the square of the averages, the square of the average. This is also equivalent to variance, but in my opinion, this is the easiest definition here to remember because it is exactly what you would end up with if you were trying to create an average distance from the mean. But we have one problem with the variance, and that's the units here, right? So the moment we squared this quantity, if our data was in units of kilograms, for example, we squared it. So now our data, our quantity here, the variance is going to have units of kilograms squared. And so now it's kind of difficult to say, we have a measure of spread. Of course, it's going to be, this value is going to be bigger for cases where the distribution is more spread out. It's going to be smaller for data that's more tightly clustered around the mean. But we don't really know, or intuitively, it's kind of hard to figure out what this quantity actually means. And it would be nice to go back to the original units that we were dealing with. And so that's where the idea of standard deviation comes in. And what we're doing then is just exactly that. We're taking the square root of the variance to get back to those original units. And so again, as with variance, we can do some rearrangements here, and you have different equivalent definitions here of the standard deviation. But this is maybe the easiest to remember. It's just the square root here. And we'll often represent standard deviation with this Greek letter sigma here. So that's standard deviation. So standard deviation then is really this idea of the average distance from the mean. But we have other measures of spread that can be useful in certain circumstances. So one basic one is the range. So the difference between the max, largest value, and the min, the smallest value in your data set. This can give you an idea sometimes of how spread out the data is. We also have the full width half maximum. So this is if we're to normalize our data and identify the maximum, the full width half maximum would be this range corresponding to the space that falls between these 2 points, where these 2 points have a height that is at 50% mark of our maximum, so the half maximum, and then we want this width here, and so this can be useful or not so useful depending on how your data looks. So it might be either useful or misleading depending on what you want to show. But so one consequence of this is that, maybe we have another peak occurring out here. This will get completely ignored, right? Because we only have one maximum. And if there are other peaks in our distribution, we're paying attention to the width occurring between the half widths or the half points of this peak. We also have other descriptors of distribution shapes. So in addition to the spread, another tool that we can use is something called the skew. And the skew is going to describe the asymmetry of data. And so this is made using the third power of x. So in contrast to the variance where we are squaring things, we're in the case of the skew, we're raising it to the third power and dividing here by the cube of the standard deviation. And so in this way, we get a value, a unitless value that is going to be positive in the case where most of your data is falling to the left side, and negative in the case where most of your data is falling to the right side of the mean. And for data that's mostly symmetric, like this case here, then the skew, which we're showing here with the gamma, the skew is going to be close to 0. So just to kind of summarize, we have these different ways that we can describe data. One of the most basic ways is to bin data, break it up into bins or buckets. And there's different ways you can do it, right? You can choose how to bin your data, and how you decide to bin your data often determines what you're going to see or how you're going to interpret that data. It's necessary when you want to visualize continuous data, for example. And histograms are a useful tool that gives you information, visual information about your data. And they're distinct from bar charts in that both their height and width mean something. And in addition to these visual tools, we have descriptive statistics like the mean. And these are ways to simplify our data into one or a few numbers. So in addition to the mean, we had the variance and the standard deviation. And the way to understand these quantities is that they're attempts to describe the spread in terms of a kind of average or typical distance that a point can be from the mean. And then in addition to these, we have the skew, which is going to be used to describe the asymmetry.